So, hello everyone. So I'm a lucky guy. I was able to set up my notebook before everything starts, so we don't have to think of this displays and can start directly. So, what is RustNN? I guess barely anyone knows because it's quite a new project. So it's a native implementation of the W3C WebNN standard. And the goal is to bring WebNN beyond just the browser to enable a unified web and desktop machine learning ecosystem so that you don't have to write your applications twice. So now I told you what RustNN is, but now you might be asking what is WebNN, because it's yet another quite new standard which is not yet fully released. So for WebNN, the goal is you have one single graph for your machine learning graph operation, and it should be able to run on any hardware which is supported by your browser. It's developed by the W3C, by the Web Machine Learning Working Group, and it just provides an API interface to define the computational graph you have to build to execute your neural network. On the right, there's a really tiny JavaScript example where you really have to say, I want to build a graph, add a matrix multiplication, add an addition. This is my input, those are my weights. You have to build everything on your own, but this way you don't have any serialization complexity in the standard by itself. And once this graph has been built and compiled, the browser sends it to some backend, which then runs on the best available hardware, which you might choose or not, depending on the browser implementation, meaning whether you have a CPU, GPU, or some NPU or ASIC or whatever installed in a browser. If there's a backend for the WebNN implementation within the browser, it can run your graph. You don't have to write any shaders. And at the moment, Chromium delegates this to Windows/ONNX runtime and CoreML and LiteRT on Apple and Linux. And this WebNN standard reached its origin trials phase, meaning we are starting to get confident that the standard is reaching a place where we can make more people try to use it. But it's still under active development, meaning there might be new operators coming or even some operators vanishing because they are no longer in use, but make the standard too complicated in the long run to maintain. So, yeah, as I said, we have one graph builder, which is great, and the platform handles the rest for you, your mobile phone, your notebook, your desktop, your node server, but it's basically browser only, or JavaScript implementation only. Is it great? Maybe we can do more. And this is what the whole talk will be about. But first, some people might say, why do we need a graph? We have WebGPU and we have WebAssembly. So why don't we just make a framework and we implement all our machine learning operations in WebGPU? And WebGPU now is working on an extension for subgroup matrices, meaning those tensor core units or whatever they're called on different hardware. And on WebAssembly, they added single instruction multiple data extensions, so you can vectorize your code. So you might think, everything is fine. Unless you start developing the most simple machine learning instruction you can have, GEM, which is matrix multiplication. Well, the first implementation, if you start, well, before AI, it would have taken you maybe half an hour to get something running. With AI, it takes you 1 minute, and then you have GEM implemented. But then you realize, my hardware is supposed to have 500 teraflops. Why do I get only 10? Because of all the overhead you have in your loop, and all the instructions and the caching and memory hierarchy and everything. So you start a loop permutation. You start, can I unroll my loops? Can I use tiling to be more cache efficient? And can I vectorize my code on a CPU? And then you might even have more control over the cache itself. And well, once you're done, you realize, I spent a year optimizing it for my platform. Now there's a new GPU architecture. You start again. So you're ending up in a really infinite loop doing machine learning through this way. There are a lot of reasons why we want to have compute for machine learning, but it's not always the best solution. If you have new operators which cannot be supported or which are not yet supported by frameworks, it is your only way to get there, and you want to go this way. Or sometimes you have really, really tiny networks and you're a company who has one network only and you can optimize for your specific hardware, it's great as well. But we are in the web browser and some web developer wants to ship some new model and tomorrow comes a new model and you want to ship it. You don't want to invest 1 year in optimization. And this is where WebGPU and WebAssembly can be problematic because you have to exactly explain the computer how to execute a tensor operation in great detail. Meaning you have to do all those optimizations. WebNN on the other side, all you put in the graph is, this is a gem. Done. And this is about telling intent to the browser instead of telling the browser exactly what to do. You're telling the browser, execute a gem, execute addition, combine those, go on with the network. And the browser itself goes through a backend and then goes to implementations provided by all the hardware vendors. Each and every hardware vendor on Windows has their own ONNX one-time execution provider running best on their hardware, including something which is NPUs. If you're going with WebGPU and WebAssembly, since you rely on a compute model described to those standards, there is no way to get to an NPU at all because NPUs have a different programming model. If you go for WebNN, you can go an NPU, and NPUs can be way more power efficient in some cases than the normal compute implementation. And I guess a lot of you use mobile phones, and you want to save power, or your mobile phone not running super hot. So you want to have the most power efficient implementation on your mobile phone if you're running neural networks. And for the WebNN standard itself, if you want to take a closer look at what it can do, there are multiple pages with samples. I don't want to go in great detail here, but the official learning group has some samples which are mostly image vision samples for object recognition, face recognition, landmark detection. So it's more on the vision side and noise suppression as well. Another big page is by Microsoft, developer preview samples, and Microsoft focused more on generative AI and speech recognition. So you can generate text, images, but they also have image segmentation. And single mode samples, if we look in the future, today we just have a few samples and we can run stuff through ONNX runtime. The killer app, I guess everyone in this room is going to use is video conferencing. And in the past, video conferencing was, oh, I have a webcam, I get the image, I send it to a server, the server does something, it comes back. But today, video conferencing is way more. So because you are so often in your home office, you might want to remove your background or blur it because you don't want everyone to see everything in your private space, privacy. Or you might want to remove it completely. If you're at home, your cat might cry or someone's vacuum. So you want noise reduction or noise suppression so that you can speak freely without any interruptions in your meetings. So another neural network to run. There's text-to-speech, speech-to-text, because you're getting the voice from the server, but then you might have an AI system because you might not listening for 1 minute and you might want to know what happened, or maybe you can't hear at all, so you want to have captions. So you need more AI to run. And the assistant to help you in the meeting is now getting more and more active in more and more video conferencing software. If you would run all those AI on your computer locally and then have not the most efficient implementation you can get, you will drain your battery. So you want to have a standard which allows to run as power efficient as possible on the underlying hardware. And this leaves us with a question, if we make such a great interface or standard in the browser which really runs everywhere so that you don't have to care about if we run on Apple, Microsoft Windows or Linux or Android or some other operating system, why do we have to limit this to the browser? Why don't we go further and say, can we do the same for desktop? Like we have with WebGPU, we have Dawn and WGPU as implementation. Shouldn't we have something for WebNN as well, so that we are able to run the WebNN tests we have on the desktop, we develop on the desktop, and then we compile and ship in the browser. Or you have 2 code passes depending on where you want to ship your application. The more you can share, the less you have to develop twice. Can we build a shared ecosystem? And this is where RustNN started. So looking at WebNN and the implementations, there's currently one implementation I am aware of, besides RustNN, and it's inside Chromium. And this implementation is so deeply intertwined with Chromium itself that you cannot use it with anything outside the Chromium browser, meaning if you want to make your local WebNN application, the only way would be to ship Chromium in headless state, pass it through. I'm not sure if this is an efficient way to do it. And well, what about other browsers? They need an implementation as well, and native applications, it would be nice. So Tarek Ziade from Mozilla started RustNN for Firefox, and it's a Python and Rust implementation of the WebNN standard. And the project is quite new, so if you test it out and you find bugs, we started in December 2025. So everything is still rough and being mangled in a good state. It started with an AI agent writing a prototype for us and extending it so that we have a working state, but now we are cleaning up and ensuring that we get a proper and nice software ecosystem based on where we started. And so I joined January 2026 after I realized, hey, this is more. And well, it allows us exactly the single deployment path in the web on the desktop. And well, I also realized we need a full ecosystem flow to meet the machine learning developers where they are today. And this is Python. We all should be honest, if someone is making a new machine learning network, it's a developer using Python, and then we want to give them the most efficient, easy way to get from Python to Rust and JavaScript. And based on this, we started to build up an ecosystem within Rust for RustNN. First, we just have a simple core. The core is a graph representation of WebNN. It has validation functionality because standards, we want to ensure that you can't put in invalid states or invalid data into the standard. And then we started to implement an IDL interface. So WebNN has an interface definition language, and we want RustNN to look as close as possible to JavaScript as well. This work started more late, but it's now in a mostly good state. So with the IDL interface itself, well, we want to have more front ends to the RustNN itself. So we have the Rust version. We have a PyWebNN, which is a Python implementation, which is not using the exact interface, but I have a PR. We have a Node.js implementation we call WebNN.js. This is largely untested at the moment. One person made us a servo fork called ServoML. He wanted to test how good one can develop software using AI agents, and used it to integrate RustNN into Servo with good success. Unfortunately, currently the integration can run only on CoreML because it doesn't use the new IDL interface yet. And we have plans, but not yet started, with a C and C++ interface, because this is where a lot of legacy software lives. And once all of this is working, I'm pretty sure the ecosystem will enhance to other languages as well. So with this front end, yeah, we need something to execute. It doesn't help if we put a graph into a piece of software and validate it. So we started with a CoreML and Open Runtime backend. And for Open Runtime, we didn't wire up the real hardware execution providers yet. It's running on the CPU. It's all fallback and validation that everything runs fine. But if we consider ONNX runtime to be a viable target because of overhead we want to try to get rid of, then we might decide to wire more backends into the ONNX runtime backend as well. We have a TensorRT backend because, well, I'm working for NVIDIA. I started to make a backend with a Rust library called Burn, which is an inference and training library in Burn. It's still in its not too late phase, I would say. But the CPU backend passed nearly all tests, and the web GPU backend as well. But for web GPU with WGPU had memory allocation problems. So there is some investigation required. And finally, yeah, we can compile to WebNN. So you can write your RustNN application going to the RustNN IDL interface, compile it to WebAssembly, and it will talk to your browser. Meaning you can write your one application in Rust, run it locally on the desktop, or you can compile it to WebAssembly and let it talk to the WebNN implementation inside the browser. And finally, well, we need tooling for an ecosystem. And currently, the path for most developers is ONNX inside the browser with ONNX runtime wrap. I will talk about it in detail later. But we think that it's way more interesting if you would have exporters coming from Torch or from ONNX and compiling directly to something which is directly WebNN, so that you know that everything you exported is really compatible with the WebNN standard and not rely on a library in the browser to validate that it can convert everything to WebNN. There's a tool inside which will be separated as our internal WebNN serialization to JavaScript, so that if you don't want to have any deserialization in the browser, you can just create the JavaScript which creates a network for you. And well, we have RustNN PT, which will go to the core soon, which is our test harness, where we run the official WPT WebNN tests. And with this, we go for WebNN everywhere. JavaScript, Rust, Python. Besides language difference, it's the same code to generate the same network. And once you got used to the WebNN operator network or operator graph, you will be fine in whatever language you are. And finally, we have WebNN graph, which is a simple serialization of the graph you are constructing with code, because if you are just in JavaScript, it's okay to have code to describe the graph, but now we want to run the same graph in JavaScript, in Rust, in Python, so we added some IDL, some serialization .WebNN, but this one we can compile to JavaScript as well, and then you can decide where to go. With a library you can use in Python, Rust, and soon in JavaScript. Okay, with all of this ecosystem stuff, let's talk about ecosystem workflow if you want to deploy a WebNN network. So state of the art today is, you are doing your network development and export in PyTorch, you go for ONNX. Then you're writing your application, and currently state of the art is you load your ONNX in the web with ONNX runtime wrap, which is a good piece of software, taking really good care of ensuring that you can run all your ONNX models. But it's still a 25 megabyte dependency you are introducing to your website, which is shipped to every user, hopefully cached. But for every different website, because now we have this cache partitioning, you are shipping it quite often potentially, which is not great. And then the other problem is each time the user is going to visit the website, it will load the ONNX, convert it to WebNN, meaning it's wasting power and it's wasting memory for the conversion. And well, you're not sure that everything will work fine in WebNN directly, or maybe there's a CPU fallback because ONNX likes to do CPU fallbacks. And well, then ONNX runtime web will either go to WebNN or WebGPU or WASM, depending on a configuration. And from there, it goes to inference backends, depending on which platform you are. With .WebNN, so with the serialization format we introduced, the idea is that you write your application, and instead of loading the ONNX, you're doing the conversion, which ran on each and every system in the world before, once on your developer machine, and you know the conversion was successful with all the operators required. And then you just load the serialization inside the website. We use .safe tensors for the weights, so that we don't introduce anything new for weights, because it doesn't make sense to add yet another standard. And this reduces the dependency to 0 to 1 megabyte, depending on what features you are going to use. If you're going with the JavaScript version, one part you lost was going to WebGPU or the CPU, because, well, it's a WebNN file. So this is, you need to implement your own fallback if you don't want to go to WebNN, or if the browser you have in your system doesn't have WebNN. But since there's more you need to do anyways, if you're deploying machine learning applications, it's not just downloading an ONNX and running it. You need to do pre- and post-processing. You need to do image decoding, color space conversions, normalization, data type conversions, tokenization, sampling, decoding, whatever comes to your mind. So you need actual code around your network anyways. And either you write all the code in JavaScript or you write your code in Rust. And well, if you're writing the code in Rust anyways, you can use RustNN to drive the network. And with the proof of concept backends we currently have, you get the same flow as with ONNX one time before, but you developed your whole application in Rust until it hits the browser. And then depends on whether the browser is Rust or not. So you're doing your export, you're generating the WebNN file, you put in the save tensors, you write your application, link against RustNN, and compile to WebAssembly. You load the WebAssembly in the browser. And then we are going through the wasm binding interface directly to the WebNN implementation in the browser, or we use one of the burn backends at the moment. This is yet to be specified or defined if it's good or not. Going to the other backend if WebNN is not available. And then we go the normal inference path. And this is a world which might give a better experience and a more power efficient experience to the users. And the most interesting part would be the browsers which integrate RustNN directly, because, well, we are going to get WebNN into the browser and we are giving WebNN back to the backend, taking care of inference. And in light-RT and ONNX one-time code passes on CoreML, we would have to convert WebNN back to those other formats and then translate it again to IHV operator sets. If you stay within WebNN, with RustNN, you don't have to do another conversion until you go to the IHV execution providers. So we try to minimize the amount of conversion steps in the whole pipeline. And some proof that this works extremely well is implemented by Mac Haggett. A while ago, we got on PR like, I'm working on getting RustNN on the Apple Watch. And I did all of this nice stuff, and he managed to generate the ML Model C text saying Apple Watch needs based on RustNN, and does the whole workflow loading.webnn to running the model on Apple Watch with minimal memory consumption. Meaning, it seems we did something correct. This backend has not been merged yet. We are working on making modular backend so that this can be used, but will not be part of the RustNN core. Coming to conformance, yeah, we have ONNX one-time backend for the CPU. This is where we run most of the conformance at the moment, and we are getting to a 99.36% pass rate for all the tests we can execute as of now. Since we don't have a browser backend, we don't have the full environment, so that we cannot run all tests, but we can run 80–90% of the tests, and all of those, except for 6 LSTM-related ones, we pass. I think this is not too bad. And we want to evaluate if we can use WebNN.js to run the full VPT test suite with RustNN to get to a full test coverage without a browser as well. This is what's next. Yeah, conformance. We want to have 100% on every backend. Browser integration. Yeah, we want to ensure that we get an updated Firefox integration prototype. Tarek did one in December, but this is most likely no longer working and was unsecure because it was in the main process, and I don't want to give this to anyone. Yeah, we need a generic GPU backend. So I have a pull request for the burn parts I talked about, but with burn we would also be able to support Vulkan Metal D3D with DXLin Alg, so we will have matrix tensor cores. And well, maybe we even try to replace the ONNX requirement so that you can ship a RustNN backend without any DLL dependencies if you don't want to get to IHV-specific EPs. And of course, we need content. The exporters are in its early prototype stage, I would say. The Torch to WebNN exporter has been developed so that we can export and run Flux to client, but we don't have a driver yet to feed the data correct in the network. The ONNX to WebNN backend has been used to export SMO LLM and some convolutional networks. It's next on my list to make this way, way, way more capable. And of course, we need to harden exporters and backends. That's it. A lot of content. Do you have questions?
Who wants to? Oh, sorry.
How consistent are the different backends with like different float precisions and stuff? So can you like, how well can you trust that you get the same results regardless of whether it goes to GPU or NPU or CPU?
Is my mic on? Okay. So the WPT tests are extremely strict, and we had the problem with TensorFlow, TensorRT, RTX, where we have something we call TF32, where we compute with reduced precision with regards to the mantissa. And we had a few tests where the WPT test said, oh, you are out of the ULP, do something better. We have to decide within the working group if we might want to introduce slightly more relaxed precision requirements, because if you are going to run to PyTorch, you will have the same more relaxed precision requirements as well. But for now, the tests are extremely strict. Do you consider it as hard requirement to be perfect?
I was mainly thinking of the anecdote of Adobe trying to move some of their stuff on Mac to the neural engine, and then they went back to the GPU because the results looked worse. So can we like expect this kind of phenomenon with the different backends?
Okay. So yeah, the current WPT tests are quite strict, and sometimes would
Yeah, hi. Thanks for the presentation. Wanted to ask about this web GPU versus WebNN comparison. Of course, WebNN uses the NPU hardware, but have some performance profiling being done on one of the backends standing out compared to the other, not only for PC, also for mobile devices?
I do not have many mobile experience, so I'm working on desktop nearly my whole experience. NPUs are supposed to be more power efficient, but sometimes NPUs have less raw power when it comes to flops per time, because they are supposed to be more tiny. So the question is, do we want to be more power efficient or more fast? Both at the same time doesn't really exist at the moment, I assume. So for...
Is there some benchmarks with web GPU versus WebNN on workloads?
I don't have benchmarks yet. I have a colleague working on web GPU gem shaders. So, you know, the cycle for multiple months now. And we are getting, so for large matrices, we are going to get close to Kublas and Vulkan performance. For smaller workloads, not yet. We have to figure out why. But this is about time. You need to spend an infinite amount of time to get to the same performance level the vendors already have in their libraries. So OpenVino, TensorRT, QNN, all of those vendors are doing all of this investment anyways. And if you have an open source project, and there are really good open source projects like GGML, Llama CPP, I really like, those are re-implementing the same kernels all over, and I have multiple colleagues working on performance in GGML on Vulkan and CUDA, doing this exact same work. The question is, do we want to have another 10, 20, 30, 40 frameworks where we do the exact same work?
Okay, thanks.
Should I go? Okay. Hi, Maya. Again, thanks for the talk. It seems like WebNN and RustNN are doing an effort to unify the ecosystem, which is great. And I saw this quote, write once, deploy everywhere, and there was this joke with Java that it's write once, debug everywhere. So what tools are there to actually debug such a long pipeline of transformations of the code? Like what debugging is available?
Okay, so in Rust, you use your favorite Rust debugger to develop your application. I don't have any experience how you would debug Rust application inside the browser. But my assumption is, since you have your Rust code fully debugged on the CPU with the same backends, depending on the browser, of course, you work on the CPU until you are done with your network. The other part is the network itself. Do you need debugging on the network if you are exporting your ONNX? I'm not sure. So we could add debugging in RustNN, of course. So the idea is that you have a mode where each and every tensor will be written out to disk for each operation, and then you can look into it. We didn't start with such a debugging mode yet, and the browser doesn't have it either.
Cool, thanks.
Okay.
Is that it? Thank you, Markus.
Thank you for your time. And yeah, I will be around. If you have questions, just come to me, ask me, and yeah, we can continue the discussion.